vertex down, 40 feet across and 40 feet deep. So identify those dimensions there.
Like the water's like where it's pulling.
So water is getting poured into the container. Imagine this as like a cup, and it's getting drained out of the bottom.
Okay.
Yeah.
How do you?
It says, well, we have a cone tank that's vertex down, and water is leaking out of the tank.
Okay.
So usually, yeah, we just assume that it's leaking out from the bottom.
Okay.
Find the rate of change of the radius of the water when the water is 8 feet deep. So with cone problems, yeah, there's our formula there, pi over 3 r squared h. And the challenge with cone problems is that there are too many variables on the right side. And we want to reduce it down to 1. Okay. And there's water inside the tank. But can we agree that the radius and the height of the cone formed by the water is always changing? So you can imagine as water is getting drained from the tank, that the radius of the inner cone is going to decrease. The height of the inner cone is also decreasing.
Okay.
Okay. So the reason that we have to build this diagram is because we would like to replace one of the variables in turn and get it down to one variable, either everything r or everything h, so that our derivative will be a little bit easier. Okay. We're on page 7.
Okay. Sorry.
So we're going to do a 2-dimensional version of this diagram. But I'm just going to basically cut it in half like this. Okay, so we can see that similar triangle relationship. Okay, so what is the radius of the cone? I mean, of the tank? The height is 40. R and H represent the inner cones. Okay, we're going to set up a relationship between R and H, and we're going to use proportions because we have a triangle within the triangle, so we can do this. We can say the radius of the small cone is to the radius of the large cone, which is 20, as the height of the small cone is to the height of the large cone, which is 40. Okay, I'm going to cross multiply here so we can get the fractions out of the way. But I still don't know which one to solve for. I don't know whether to solve for R or to solve for H, but we can make that decision later. But so far, we've gotten to the point where we can easily adapt to whichever variable we want to solve for, either H or R. Okay, so let's gather some information from the problem to see. We already got everything we need from the first sentence. Second sentence, the water is leaking out of the tank at a rate of 80 cubic feet per minute. So question is, what is that referring to? Which variable is that referring to? We don't see that variable yet, but say it again. Volume. Okay, so we definitely, how do you know it's volume related? Okay, and something else though. Something else is giving cubic feet, right? Cubic feet, that is a volume dimension, right? Cubic feet, that's a 3-dimensional unit, so we know it's volume. But there's something else here. This is not just volume.
It's the radius. No, that. Yeah, the radius and the height is getting less.
Right, but we're talking about which variable is that referring to? So the 80 is not actually, yeah, it's actually not referring to V, it's actually referring to dV over dt. And how do we know there's time involved with this value?
Rate.
Rate, okay, and it says per minute. Okay, So cubic feet per minute, that's volume and time. So the only variable with volume and time in it is dV/dt. So we know dV/dt. Now, is there an adjustment we have to make with that 80? Negative. Why negative? Okay, so the volume inside the tank is decreasing. So it's decreasing by a rate of 80 cubic feet per minute. Okay, find the rate of change of the radius of the water. What are we looking for? dr over dt. You know, you see the word radius, so it's obviously related to r, but then you see the rate of change of radius, so it can't just be r, it has to be something related to r, so that's right, dr dt. When the water is 8 feet deep. Height. Now, is this height of the water level always staying at 8? It's always changing, right? 1 minute could be 7, next minute could be 6, then it could be 5, then 4. So what we want to be careful about is that we don't want to use this 8 too early. Okay, if we use it too early, then we're telling the problem that this height is never changing, which is not true. So what I want to tell you about this is that we are going to use this, but not at the beginning. We're going to do not use until the end. Okay. It is going to be useful, but not until we've established a moment in time. But right now, we're still in the variable stage. All right. Now, let me put the volume equation here again. Okay, so we have a decision to make. We have to decide, do we want to get our volume equation on the right side in terms of R or in terms of H? Okay, so here's the clue. What are we looking for? What are we trying to solve for in the end?
dr.
dr over dt. So dr over dt is related to what? Yeah, to the radius, right? So rate of change of the radius. So which variable will be more straightforward in terms of which variable will naturally produce the dr dt, the r or the h? The r. So we would like to remove and replace the what? Replace the h, right? That's the hope, right? If we can replace the h in terms of r, then we can find the derivative, and then the r will naturally produce the dt. Okay. So if I want to replace h, then what should I solve for? Yeah, I should solve for h. Okay, so how can I solve for h? Okay. So what's h equal to? 2r. Okay. So I'm going to make this substitution here. Everywhere I see the h in the volume equation, I'm going to replace with 2r. So now we're going to rewrite the volume equation in the variable that we want to represent. Okay, so v equals pi over 3 r squared times what? 2r. Okay, any questions so far? Now, we do want to find the derivative, but the thing I've seen with students is that they want to find the derivative too early. Okay, you could find the derivative, but two mistakes that students make is if they recognize the need for product rule, they'll go through product rule, and it's not worth the effort to go through product rule. Or they go through power rule, but then they do these separately. Okay, we can't do power rule separately because these are being multiplied, but we can merge it all into a cleaner expression and then just do power rule once. Okay, so how can I clean this up so that My coefficient is together and my variable is together. We don't have to, because these are the same variable, right? We can merge. Now, if it was like R and H, like we saw here, then we have to go through product rule, but we have a way around it, right? If I have the same variables, I should be able to merge it together. Yeah. What would that look like? 2R to the third, okay. No, but we can keep going. I'm gonna make that look even cleaner.
2R to the third over 3.
What if I put all the coefficients together and so I don't have to stare at a number below the variable? It just makes the power rule process a little easier. No, that's too messy. Idea. The way it is.
Oh. We did it.
Yeah. Yeah.
I know what to do. I don't want
Let's say it. Just say it. Yeah.
because the H equals to 2R's and the H equals to 8, so do 2R equals 8 divide R by 2.
Not yet, not yet. But I'm just in terms of this though, how can I rewrite this so that I can just make it a little cleaner to.
Oh, 2 pi over 3.
Yeah, so I like to put all the numbers together. And then the variable by itself. If you put the number under the variable, I see students they get a little confused, like, wait, what do I do with that, right? But if I see a number in front of the variable, it just feels cleaner. I know that's not going to go anywhere. My power rule is with the R cubed. So, you can do 3 to the -1. You can put the 3 under the R, but it just doesn't look as clean, and it may hamper what you recognize as the next step. Okay, so now this is where we want to be before we find the derivative, right? It's a lot cleaner here than here. Prefer to make the calculus step as easy, as clean as possible. Okay, so now let's find the derivative. Every variable gets the time treatment. So what does V become? Derivative of V is, 1 dV over dt. Okay, the 2 pi over 3 is just a number, just a coefficient. It's attached to the R, so it's going to stay in the problem. The power rule is with the R cubed. What's the derivative of R cubed? d over dt. Every variable is going to have a time component to it. Right, so that ends the calculus step. From here, we're just plugging in and finding whatever variable we're looking for. So any questions doing the one calculus step in this problem? Okay, what can we do to maybe further clean this up before we plug stuff in? Okay, but in terms of this expression though, or this equation, is there anything we do to just make this a little bit cleaner to look at? How about this side, just this right here? You see anything that we can clean up? Anything that can cancel out? What about this 3 and this 3? Because one's in the denominator and the other's in the numerator.
Okay.
Right? So it's like 1/3 times 3, right? 1/3 times 3, which is be 3 over 3, which is 1. So it's the same idea there. Does that make sense?
Yeah.
Okay, so let's look to see what we have. Do we have dvdt to plug in? We're looking for drdt, so that's there, right? But do we have r? No, we don't have r. We don't have radius of the water level, but we do have the height of the water level. They're not the same thing, but they're related. So what is something that we can use to help us convert from that 8 height of the water level to the radius of the water level? There we go. Yeah, there's our formula, right? So I can plug 8 in for h and solve for r that way. So r is equal to 4. So now everything we need is ready for us to use. Okay, so dvdt is -80. Okay, we'll divide this over to the left side, to the other side, but first I want to get this to be a little bit cleaned up. So 16 times 2 is 32. Okay, next step. Divide by 32 pi. Now, if you want to put this in the calculator, you can, just don't put pi in the calculator. Once you put pi in the calculator, it's going to give you a decimal approximation, and I want exact values. So you can use the calculator to reduce that fraction, though, if you like. We know that 8 can go into both numerator and denominator, so I get -10 over 4, which can reduce even further. I can make this -5 over 2. Now, where's the pi located? Denominator, yeah. So I know it looks like a strange place. A lot of students want to bring that pi up because it looks more correct, but that pi needs to stay in the denominator. If you bring that pi up to the top, instead of dividing by 3, you're multiplying by 3.14, and that's a different number. So drdt is -5 over 2 pi. Okay, what's the unit of measure here? Now, cubic feet is for volume. Radius, is it a 1-dimension, 2-dimension, or 3-dimensional unit?
It's
1 dimension. Yeah. So what's radius? What's the unit for radius?
Oh, it's just speed.
Feet, and then time is,
Minutes.
so that's your unit, feet per minute. So if you ever are asking, wait, what is the unit? Look at the variable. The variable will clue you in as to what you're going to involve to build your unit.
Wait, why? Why is the variable clue?
Because you have r and you have t, so that reminds you, oh, I need to find the unit for radius, I need to find the unit for time, and I need to divide them over each other. Okay, and does it make sense that we're getting a negative drdt? Decreasing, right? The radius, as water level is dropping, you expect the radius to be getting smaller. So I think this is the most intensive in terms of steps. Yeah. So we'll do this again in class since well, first I think to finish with you guys because
Yeah, I'm get rid of this one.
Yeah, we didn't. And also we didn't finish the problem before it. So
Because we're good.
yeah, after doing the finishing it. So do you want to try another one of these or you want to look at a different type of problem? The cylinder, I'm gonna go over as a class. We haven't gone over
Oh.
this cylinder yet. There's a different process with cylinder. So, yeah. So we can either do volume of a cube, volume of a sphere, or we can do another cone problem, or a ladder problem.
You know how to do 38.
Uh,
That's like the ladder problem.
yes, yeah, for the first part, but then when we get to C, I haven't talked about theta, so yeah, I think 38 was not supposed to be given for you. It's all right. So either 9, 10, or 23. That again? 23, okay. That's good because now we can see how we line up with our steps, right? Now that you've seen all the steps, it's a different process. Trying it on our own versus following along, right? So see if you can start the steps and then I can follow up and go through it with you.
Did you make the proportion? Again?
So I did a right triangle within the triangle. And then the R and H are the same. And then I start to do the radius of the container and then the height of the container.
Okay.
Last night.
Mm-hmm.
So like on here, when it says volume, it has this volume equation. Why is it that sometimes you put pi over 3 r squared h? Would you just multiply the pi?
Yeah.
Like to make it one less step.
Yeah, I like to have that pi with the 3. So it doesn't feel as there's that many pieces. Yeah.
Okay.
Okay. What do we? Okay. What do you guys have so far?
I'm stuck because I find it really hard to clean up when you plug in what you got for the proportion. Like what I was confused on last time.
Which part?
I got to. Okay, you solve for H, right? First, trying to find the height. Or you're trying to find, you're trying to find DH over DT.
Yeah, I'm trying to find DH over
So you
DT.
solve for H by making a proportion, like the last one. Or you do something different.
Well,
I got H equals 4.
yeah, so let's explore that. I think what you started off is right, but let's gather some information here, just so we can just have everything in front of us here.
Okay.
So you're good here, all right? 16R equals 4H, you get that far.
And that's where I got, and then I tried to simplify, putting it in, or clean it up after I plugged in.
Right. Okay, so right now we're still not ready to know which variable to solve for.
Okay.
Okay, so let's gather that information here. Water is poured through the container at a constant rate of 16 cubic meters per minute. What information is that?
That's, at that point, the radius and the height would be changing, right?
Well, what variable is this referring to?
Feet, so it's volume.
Is it just volume?
It's volume over time.
So dV over
dV
dt.
over dt.
Positive or negative? Right, because
Because it's increased.
right, how fast is the water level rising? What are we looking for? Okay. When the water is 8 feet deep or 8 meters deep.
Still high, right?
That's height. Yeah, this one is height. What we're looking for is DHDT, but we have 8. Now, this is the height of the water level. Okay. Is this always staying at 8? So it's changing, right? So we want to hold off on using this till late, right? So do not use until late, until the end. Okay, let's explore the volume equation here. Okay, so we're looking for DHDT. So what variable do we want to keep? H, which means we want to get rid of the R. So which variable should we solve for so that we can get rid of the R?
H.
If we solve for H, then H equals 4R. Then I replace H with 4R, then everything's in terms of R. Okay, let's try that. So R is equal to 4H over 16. R is equal to, what is that? What's R equal to? H over 4. So if I make a replacement here, will this get rid of my R? Yes. So I think what you experienced was, yeah, you solved for the wrong variable, but it was hard to catch yourself because you didn't know why or what your end goal was, right?
Okay.
Your end goal was to hold on to H, and when you got rid of H, everything fell off, right? So we kind of have to kind of revisit, wait, maybe I didn't quite solve for the right variable, and we kind of revisit it from that perspective. Okay, so now we can do pi over 3 times H over 4 squared.
We get. Okay, yeah. Okay, I'm good.
So basically, when you're doing that, you want to find the H or the R, like you want to find the one that when you plug it in, you're only left with what you're trying to find.
Exactly.
The derivative.
Yeah, it does feel a little confusing. You're like, wait, why am I solving for R if I'm trying to get rid of it? Because I basically think of it this way, I want to find a replacement for R. So that's why I'm solving for R, so I can replace the R with what I really want in the equation. Okay, there's something else though in my volume equation. Times H. There's the H here, okay. So we don't want to do, so our first goal is taken care of. We took care of the replacement. We don't want to do our calculus too soon, okay? Because if we forget about the cleanup process, we're going to mess up on the derivative side of things. So now it's cleanup, okay? Let's get everything cleaned up. Let's get all the fractions nicely compacted together. Let's get the H's together. So it just feels like a nice, clean power rule problem. It should look very manageable. It shouldn't look messy. So let's see if we can work our way to that point. Okay, so what would you do too? Okay, all right. Pi over 3 times H. Okay, keep going. How can I get this even more cleaned up? Okay. So 3 times 16 is 48. So what that look like? Okay. It should look, as every cone problem should look like this in terms of how clean it looks, right? It should feel like, oh, this is an easy derivative problem. We should always be saying that when we reach our, right? If we're looking at this going, let's find the derivative, it doesn't feel like an easy problem, right? So the way that you know that you've gotten it cleaned up is it looks easy. Okay. You can, it's just I prefer not to look at a number below the variable. It just feels like, wait, do I need to do quotient rule with that? And it just feels a little bit, because if I can just treat this like some number that just happens to be a fraction, it just feels cleaner. I can just kind of separate those parts. Okay, so when I'm ready for the derivative, v becomes okay. We can go ahead and plug stuff in, or we can clean up. It's up to you. So if you want to go ahead and plug in, you can, because everything is in front of you. So dv dt is 16. H is, now we can use it. You see that now that we've established our derivative, we're ready for our very final portion of the problem. now we can involve the 8. We don't want to use this 8 before this point, though.
Why can we use it now? Like, I don't
Mhm.
understand.
So now that we found the derivative, everything is set in stone. We've built a relationship. Now we're just trying to figure out what is the volume at this moment in time. But before this point, we haven't established that relationship yet. We have to hold on to our H, because if we replace our H too soon, that means we're left with no H. And if we're left with no H, there's no chance that a DHDT will pop up. Right, so the only way to get DHDT to show up is if you have H to begin with, so they can actually find the derivative and actually get it to show up. Okay, so now that we have the derivative, and now that we're looking for a number, we can put that 8 in for H. Okay, so power 48 times 3, what? Okay, so we got to clean this up here. Ideally, I would like to merge this together as one fraction first, and then I can worry about how I can bring it to the other side. Okay, so 3 times 8 squared, that's 3 times 64. You say 192? Okay.
And you gotta bring it over, so instead of dividing it, you bring it over, but you multiply it. So
Okay, yeah, reciprocal. Feels easier than having to do a complex fraction, right? Okay. Where's the pi located? Bottom, yeah. So when everything is said and done, just make sure that pi is still there at the bottom. It's not always the case, but a lot of times it is, especially with these problems. So now I'm just trying to clean this up here. 16 times 48, I can multiply that out, divide by 192, see if that will give me a reduced fraction. Also, we get all the way down to 4. So what's my answer here? Which part?
Are you just simplifying? Like,
Yeah, I'm just multiplying. 16 and 48 is 768 divided by 192.
did they keep it on the bottom?
Yeah, it does stay in the bottom. It feels like that pi can just come up, right? Make it 4 pi. But
It's technically like even 192 into 768 4 times. You
Yeah.
get pi and then go.
Pi's not going anywhere, right? Right. What do you think about it this way? 768 divided by 192 is 4, but how about 4 over 1? And then that pi is still there. So yeah, it feels like, oh, all the denominator is gone, so the pi should come up with it, but the pi is still down there. Okay, what's the unit of measure here? Okay, meters for height, minute for time. Does it make sense that I'm getting a positive DHDT?
that's just the simplified version of
Yeah.
6.
768 over 192. 192 goes into 768 evenly 4 times. Okay, does it make sense that DHDT is a positive value?
Instead, go sort of like traffic always so bad.
Yeah, understand. So why is it positive?
Because the water,
Well, water is rising, so everything's increasing, right? Height's increasing, volume's increasing, radius increasing. Okay.
question on 35.
Yeah.
I understood like how to do the problems. Like from the key, I just found the Y's, but so you have like the diagram theorem. You have the 8, and then you find the x's from A, B, and C.
Mm-hmm.
But. Oh wait, never mind. Never mind. I think I figured it out.
Yeah, yeah. Everything is staying this, oh. X, Y. Yes, okay, see ya. It's a little tedious because you have to kind of basically redo the problem 3 times. Each time, because it's a different X value, but yeah, if you know how to do A and then B and C is just repeated process, yeah.
I just started doing 38, I was like.
I know, I should have